I have 3 case studies. What we'll do is I will describe the problem very briefly, and we're just going to jump into the PCAPs, right? So I've got 3 of those, and then afterwards we'll talk about some takeaways, which are just kind of my couple thoughts about it, but really it's about you. Whatever your takeaways are, as we go through these case studies, write them down or tattoo them or whatever works for you. My name's Kary Rogers. I'm the Director of Staff Engineering at Tech Support for Riverbed. I came up through TAC, answering phones, helping customers solve steelhead optimization issues. Maybe it's not as fast as it should be. Maybe it's broken. Why is that? And I found that the quickest way to solve a customer's problem was looking at the packets. Some of my colleagues I found were a bit slower, and because they weren't that as good at looking at packets. So I found that the better I got at it, the faster I got at doing the analysis, the quicker I could solve the customer's problem. And I also, if you remember Gerald talking about programmers or being lazy, I know enough to be dangerous. When I first started working at Riverbed, we have some proprietary protocols, and we were like, they taught us to read the offset, that's the address, this is the port, and do that by hand. I was like, no, I'm not doing that. So I wrote a dissector for that protocol, and I convinced my boss back in 2011, 2010 to come to SharkFest. I kind of walked in thinking, I know what I'm talking about. I'm a packet guy, and I was blown away. Seeing the guys that you see present, Jasper and Hansang and Christian and all these people, I've learned so much from them, and so you're going to take a little bit from me, which is parts of them, and you're going to build your own process, but that's what we're here to do. If you have any questions, just shout it out, because I'll be looking at the screen mostly and not at you. No offense, so just shout out if you have any questions along the way. Anything else that I'm forgetting to say? I don't guess so. Oh yeah, so 3 case studies. One I did in the summer at the SharkFest US, but the second 2 are brand new. No one's ever seen them, except for one person here who gave it to me. So I have not done those 2 in public, so bear with me if it's a little rough, but I think you'll find them interesting and it'll be fun. So, the Packet Analysis A-Team. The Packet A-Team is what I call it. I have a little website called packetbomb.com. I am now the Director of Staff Engineering. I think I mentioned that. So I'm a manager now. That means I've lost all my technical knowledge, right? It just automatically that day you get the job, it's gone. But I tried really hard to hang on to packets because I really enjoyed it. I liked doing Wireshark and doing packet analysis, so before it all slowly drained away and went into nowhere, I thought I could put some of it on the internet. So I have this website called packetbomb.com, and people find me, email me. Sometimes I find them if they post about problems on Reddit or something. Give me a PCAP, let me see if I can help. So if you're familiar with the 1980s American television show, the A-Team, that's kind of, if you have a problem, no one else can help. If you can find them, you can hire the A-Team. So that's kind of the thing. How do I start this?
Thousands of people turn to the internet for help because they have a burning computer and network problem that they cannot solve. If you have a problem, if no one else can help, and if you can find them, maybe you can hire the Packet A-Team.
All right, yay, we're all the Packet A-Team now. So, before we get started, let's talk about, I repeat these things almost in every PCAP, every case study I do. Things that you should do, I think are important. Again, you take away your own process, but these are things that I think are important. If you're gonna when I walk around at Riverbed Support and I see someone looking at packets and they have the default layout, I have to stop, take a deep breath, not slap them upside the head and say, let's help you out here. If you're going to add one thing, if you're going to do one thing only, you need a delta column. It's very important when you're looking for problems, when you're looking for performance issues, that you add a delta column. And we can just go to Wireshark real quick. Can you guys see that? Oh, by the way, if you're in the back and you're having trouble seeing, sometimes I get that feedback. Let me know, and I'll tell you to move closer up. Or I'll make it bigger. Maybe both. Should I make it bigger? Is that okay? What? In the back? Good? Okay, cool. I don't want to hear about it on the survey. Okay, column, delta column, right there. All you have to do to add columns is find the thing you want. Nifty thing about Wireshark is if you see things that are in square brackets, that is information that is not contained in the packet itself. It is something that is displayed for your benefit that Wireshark presents to you. So when you see, like in TCP, you can see the calculated window size versus the window size that's in the packet. If you look at the bytes, that's actually in there. Calculated window size is not in the packet. The other one is next sequence number is a good one. You have sequence number. That's right there in the packet. Next sequence number, it ain't. It's calculated for you. So if you want to add something, you just right-click on it and apply as column. So delta, you should do that. What else we got? Statistics. When I get a PCAP from someone, especially strangers on the internet, I don't really know what I'm getting many times. So what am I looking at? I'll go to the conversations and hope that it's, if it's a throughput issue, hopefully there's just one connection, not like tons of them. This has two, same addresses, but one's small, one's large. That makes it pretty easy to jump in and see what we got to do. Three-way handshake, and this is going to come up all throughout. It's very important. It's very important that when you're capturing your data to analyze a problem, you get the three-way handshake. There is information contained in the three-way handshake that's only there, and if you miss it, it's gone forever into the night of the internet. You will never see it again. So always get the three-way handshake if possible. I understand sometimes it may not be because it's got good information like the TCP options about what's going on. And from this, you can determine the round trip time, and you can figure out if you've captured on the client side or if you've captured on the server side. So for this one, which do you think, which side have we captured on? The side, the client or the server? On the server side, I heard. So if you think about it, if I'm the client and I want to talk to a server over there, and let's say I'm capturing on the client, you see this SYN go out at time 0, right? Time 0, we capture the SYN, it goes across to the server. The server gets the SYN at time 0 for itself, right? SYN shows up, it immediately sends a SYNAC back. There's very little delay, if any, between the SYN and SYNAC on the server side. The SYNAC has to go back across to the client, where the client has been waiting this whole time. So there's a delay between the SYN and the SYNAC on the client side. He finishes the three-way handshake with an ACK, so it goes back to the server. You're earning your keep here, keeping up. And the ACK shows up. And so there's a delay between the SYNAC that went over there and the ACK that comes back. So the delay is either between the SYN and SYNAC for the client side or the SYNAC and the ACK for the server side. And we can see there's just a few microseconds between the SYN and SYNAC and about 9 milliseconds between the SYNAC and the ACK. Round trip time, we've got MSS information, SAC, all the good stuff you want to know. And window scale is very important. You don't know what the true window size is if you don't get the three-way handshake. And then When I was doing packet analysis every day, if I would have to look at TCP stuff, I would have to look at layer 2 stuff, I would have to look at pretty much every layer, really, and different protocols, HTTP, SMB, and so I would have a profile for whatever I was troubleshooting. And you can easily switch between profiles down here, and I recommend that you create a profile for what you're doing, save it, and you can switch back and forth. Since I only do this occasionally, when people email me, I tend to just go with my default and then just add and tweak as I go. But that's just me. Okay, so I think those are the things I generally talk about with each case study. I just want to go ahead and get that out of the way. So let's get into the first one. This was someone who they had a sparkly, brand new 1 gigabit connection from their data center to AWS. But they weren't getting the throughput they expected, and they wanted help figuring out why they weren't getting throughput. And as lots of people like to do, they will use iPerf to test. If I had $1 for every time someone was chasing some problem they thought was wrong with their connection, their WAN, when it's really just they're not using iPerf correctly, they're not setting window sizes. Anyway, so I'm thinking, well, you probably just aren't using the config properly, but let's have a look. So we already looked, but we'll do it again. Again, I get my PCAP. Someone emailed it to me. Let's see what we're dealing with. Look at my conversations, and I have 2 conversations. One's just 28 packets, a couple thousand bytes, and the other one is 200 meg. So if you've looked at enough iPerf, you can spot patterns in how it behaves. So iPerf2 will start the connection. I think it'll send like maybe 24 bytes back and forth where it's just setting up the parameters of the connection, and then the data goes. iPerf3 has a separate, I guess, sort of like FTP behavior, where it has one connection where it talks back and forth, and a second connection where it does the throughput. So our three-way handshake, we've already determined that we have around 9 seconds round trip time filed away. As you do your analysis, you're just tucking information away and you're bringing it back when you need it. The title of this is receiving, so they're receiving data, but it's also the, quote, server side. We can see that we have 1460, MSS size, we have timestamps, window scale, all right. And on this side, smaller window scale, but we have 1460 the same. You notice any differences between the SYN and SYNAC options that are important? Any differences? Yeah, the timestamp. The window scale is different. Does that matter? They're in different order, right? Whoops. They're in a different order, right? Does that matter? Don't know, probably not. Again, things you just kind of file away. Things you might notice that may come back and be important, maybe not. And as the more and more you do it, the more you learn to sort of say, and throw away the things that don't matter and kind of hold on to the things that do. So then we have our second connection. Just to take a quick look, it looks pretty much the same, right? Same round trip time. So, and then we have the data starts. So we'll just take a little leisurely stroll through the packets. Now this is a lot of stuff, right? This is what I use. There's a lot of data. And so this is what I find important because I know what I'm looking at and I know when to look where. If you're just starting out, maybe you don't have all this on there. I think it's really important to be able to do sequence number analysis, and people don't always learn how to do it. I remember a guy posting some TCP dump output on maybe a Reddit thread, and someone made a comment about the sequence numbers. And another person said, I've been looking at TCP dump output for 15 years, and I've never bothered with sequence numbers. Like, what are you doing then? I'm sorry you wasted 15 years of your life. So I would say, probably keep it down. Maybe you take out the sequence number stuff. I have sequence number next, sequence number ACK. The window size, bytes in flight, which we'll talk about. Push bytes, which I don't know if I'm going to talk about it later, so I'll tell you now. Bytes in flight is how many bytes have been sent but not acknowledged at any given time. Since this is the receiving side, and it's acking as soon as they come in, packet, packet, ACK, packet, packet, ACK, the bytes in flight don't get up very high. Push bytes is how many bytes have been sent since the last push flag. Because the push flag can sometimes give you clues about the application behavior, how it's written, the buffer sizes in the application. I don't think that comes up in our case studies today, but some of my previous case studies, it's been very important. So I have this little blue coloring line for push flags just so they jump out. But you can see, right, you see a pattern as you scroll through. Nice, as one ACK for every 2 packets. Standard TCP behavior, right? So good. Now, when I'm looking at throughput, my favorite tool is under statistics, TCP stream graphs, and Stevens, just kidding. TCP trace. Let's embiggen. Okay. What we have here on the x-axis is time in seconds, and what we have on the y-axis is sequence numbers. Sequence numbers are just the way we keep track of the bytes that have been sent. So one sequence number means 1 byte of data. So really it's just bytes. So we have bytes over time. That's throughput, right? So we want to see it go up and to the right, which is what it's doing. It starts down at time 0, time marches on, we send more data, so it's going up and to the right, pretty nice and smooth. Is this a good graph? I don't know. Probably not, since we're not getting the throughput that we desire, which you can look under the properties and see that we're getting 163 megabits on average out of our 1 gig pipe. So let's zoom in, have a look at the beginning, and we can see that, and this is a stream graph, so it's, a stream is one direction. So you have to click on a packet with data on the side that's being sent to see anything, because if you do it the other way, you don't get anything. So if you bring up this graph and it looks like that, just hit switch direction. Zoom in, and we can see, all right, let's talk more about what we're seeing here. So these little guys are the packets, right? The bigger the little line, the little I-beam thing, the bigger the line, the more data that's in that packet. The green line below it is the acknowledgement. So when it goes up to meet and they're on the same level here at the top, that means all of that data has been acknowledged. We get 3 more packets, the green line goes up. That means these 3 packets are acknowledged, these 2 packets have been acknowledged. And then we have nothing happening. Why is nothing happening? What is this behavior for TCP at the beginning of a connection that you see? Some data, some more data, some more data. I think I heard someone say slow start. Slow start. We keep increasing the amount of data that we're able to send in one go, the congestion window size. The receive window is advertised in the packet. You can click on it, you can say, okay, this guy says he can take 64K or whatever it is. But the congestion window, which is how much the sender thinks he can send based on the current conditions of the network, et cetera, is not advertised anywhere. You can't see it, you just have to intuit it. It's not in the packet. But we can see that it's per round trip, right? It's around 9 seconds, milliseconds round trip. So we send some data, we've sent all that we can send, we wait for the acknowledgments to come in, then we can send more. The line at the top is the receive window. This is how much space is available in the receive buffer of the receiver. So the distance between the data and that line is how big the receive window is, right? So there's plenty of space here, so we're all good. So we keep sending more and more data. Zoom back out a bit. And it just kind of keeps going like that. It's just kind of like a little wobbly up and to the right. Just real consistent. Data coming in, but not as fast as we think or that we want. So it seems like the sender maybe isn't sending data, because we've got plenty of receive window room, right? The space between the data and the receive window line. We're not filling the receive window here. So why aren't we sending more data? Well, what we can do, let me close these from a previous thing. What we can do is have a look at the sending side. Sending iPerf. So just to do a quick sanity check on this, look at our conversations. It's the same two. We've got our two connections over here. And we'll see if everything looks as we expect. Well, something does look a little different. Do you notice any differences from the previous capture file in this one? Maximum segment size. It's different, right? It was 1460 in the other one. Is that a problem? I don't know. Probably not. But again, you file it away. We know that when it was, so we know this is the side that is initiating the connection, right? We can verify that. Look, there's the round trip time after the send. So this is the side initiating the connection. So this is his, we're capturing on the host, probably, yeah. So he's sending 8961 as an MSS, but when it arrives, it's 1460, right? That's something adjusting the MSS, probably a router or something along the way, adjusting it to the correct size for the MTU. So that's fine, probably. And 1460 is what we get back. All right, so let's do our little scroll through. Let me just kind of get there. Doing our same scroll, this looks different, right? How does this look different from the pattern we saw before versus now? Before, we saw data, ACK, doing the nice little TCP dance, right? Well, here we see several data packets going out, and then the ACKs coming in later. So it's important when you're doing your analysis, one, you make the recognition of where you captured, client or server. And depending on that, it's going to look different, right? If you're receiving data, as soon as two come in, you send an ACK immediately. Data, ACK. That's what it looks like from the receiver side. From the sending side, I can send, in slow start at the beginning, maybe I can send 2 packets or whatever. So I'm going to send those 2, wait for the acknowledgement. Now I'm going to send 4. I'm going to go ahead and send them because I'm allowed to send 4. It's not going to fill up the receive window. So I send all 4. and it takes a round trip time for the two ACKs to come back, to ACK those 4 packets. Now I'm going to send 8. So I just shove all 8 out the door at once and wait for the acknowledgments to come in. And the acknowledgments will then, as you send more and more data, the acknowledgments will start rolling in, but you can see from the sender side a bunch of packets go out at once before the acknowledgments start coming in. So again, think about the perspective of where you're capturing and what it should look like. So we'll scroll down until the dreaded red and black lines. TCP window full. We've talked about receive windows. We've talked about congestion windows. I can only send enough data, bytes in flight, up to the receiver's receive window, its receive buffer. And in this case, here's the ACK right here from the receiver. 212.992 is its receive window. Look at the bytes in flight. We're sending, and then we hit 212.992. We filled the window. We are not allowed to send any more data. So we have to stop, and we wait for the acknowledgement. The acknowledgement comes back. Now we can send 2 more, right? Because an ACK is ACKing every 2 packets. So we send 2 more, and now we filled the window again. And you notice the bytes in flight went down, and now it's back up to the receive window. So let's see what this looks like in our favorite graph, TCP trace. We'll zoom in. We have our slow start happening as we saw it before. And then pretty quickly, essentially after like 1 round trip, no, that's not right, but pretty quickly, before I told you if the data's down here and there's space between the data and the receive window line, that's the amount of space you have. Well, if the data is touching the line, that means you filled it up. So you can determine that just from this pretty picture. So we hit that line, we have to stop. We have to wait for this data to go, some of the previous data to go, and then get acknowledged, and then we can send 2 more, right? We send the 2, and then we have to wait. Zoom back out. And we send some more, and we hit the receive window, and we have to wait. And so this is happening over and over. So we are clearly receive window bound on this side, from this perspective. But we didn't see it on the receiver side. We didn't see it there. And you also notice that when we're sending the packets, especially down here, it's like, it all goes down in one go, right? And the other side, it just looked different, right? It's kind of spread out with a butter knife, right? A little more even. So that was like, When you're sending, right, you are dependent on the ACKs coming back to tell you that you can send more data. So getting the ACKs back in a timely, on time, like a clock, is important for you to keep that transfer going and keep the throughput up. So I want to see, like, we know the round trip time is like right at 9 milliseconds. How long is it taking to ACK the packets that we send? So we're looking from the sending side, and you can add a column, which I already have in the past, I'm just going to enable it, but it's the round trip time to ACK a segment. And you can find that, I believe it's in here? Yes, under the sequence ACK analysis section. Here, you can right click and you can add it. So what I'll do is I'll sort by this value and then go down to the bottom and see what we have. All right. So this is the axe coming back from port 1025. And we've got 60 milliseconds, 40. I mean, it's a lot higher than 9, right? A couple longer ones from our side, which we can dive into if we want to see where that is. But there's a lot of acts here that are higher than round trip time. And another way to look at this in a pretty picture is under the stream graphs, you can look at round trip time and switch directions. So we would expect, these are the round trip times for all the acts. So we would expect it to be kind of clustered around 9 milliseconds, which, it's down here. But there's also quite a lot that's higher, and some way higher. And there's a lot of variation here, but clearly there's something causing the round trip time to be artificially increased. So if we go back to the other one, the sending side, just to see, and we sort by the ACK round trip time. And again, this is a side that's sending the ACK, so it should be really short, right? And we have a few high ones, so we can look and see what those are. And then we have some round trip times from the other side. That's okay. But the ones we're sending are all, in the microsecond range, which is what we would expect. So it's not the sender that's delaying the acts going out. And we can see what these are by clicking on one, sorting it back. Why did we take 50 milliseconds? And we are here. Did I do that right? I think it's backwards. Okay, there we go. So this is an ACK. At the end of a connection. So here's a fin for that port. So I'm probably not too worried about a delay towards the end of the connection. It's not somewhere in the middle. So to wrap this up, because we have more to do, something in the middle, because these captures are taken on the edges of the network, the sending, or maybe they're taken on the host itself, but you're taking on the host, the two hosts, doing the iPerf. Something in the middle is delaying the packets. What kind of things might introduce delays like this? What's that? Shaping, yeah. QoS, shaping, some big buffer. These packets are sitting in a buffer, waiting to get on the freeway, in a parking lot, waiting to get on the freeway. It's being, the throughput is being spread out, as we see here. They're not all together. They've been spread out, and the acts are being delayed, so that's slowing everything down. So this is the feedback that I gave to the person. Like you have a configuration somewhere, you have a buffer somewhere that you need to find. And if it's your network, you probably know the likely candidates, where to go look if you're not sure, or you may have to narrow it down. You keep moving in or out, depending on your perspective, to figure out where that's happening. Or maybe you have to go to your provider. Like, what are you guys doing? You probably know what you pay for, the service that you're getting. You can raise the issue with them. So this, I went back to this guy. They agreed that it's definitely a buffer or a deep buffer, a config. And then his group sidelined the project and they left it. So good stuff. All right. Let's go back here. Any questions on that? Oh, we did that. So, round trip time, MSS, window size, capturing a three-way handshake so you know what the window size is critical. And again, think about the behavior, what you're seeing in the capture based on where it was captured. So if you're, we talked about this, if you're receiving data, the acts go out immediately. On the other side, you're sending a bunch of data at once. Think about the perspective of what it looks like. And then know a little bit about the application behavior. If it's iPerf, what do you expect to see? 2 connections, 1 connection. Make sure you've set the window size, the -W in iPerf appropriately for the BDP of the link, or you're never going to fill the pipe. Okay, so we'll do another quick video that illustrates some TCP basics. No, play. All right, that's my now 6-year-old daughter. She's a delight. So we're don't want to run out of time. So NFS hang. This came from a buddy at he works in support for a different company. He knew that I did packet bomb. He's like, hey, can you help me look at this? We got an NFS hang, some kind of TCP issue. We've got, what is this? Susan Linux. How do you say it? Enterprise 12 on bare metal talking to a NetApp that's serving up NFS. They tested it with other flavors of Linux and didn't see the issue. So that's a big clue, but we still need to understand what's going wrong. And then they have IP connectivity when it hangs. They tested, they do some pings. They're still talking, it's just that this connection has hung. So let's have a look. This is going to take this actually first. So I'm in the directory where we have it. Now these files he gave me, NetApp captured, I think, on the NetApp, and then the SLES12 PCAP captured on the server. And you can see one's 1.5 gig and one is right at a gig. Wireshark's not going to like that very much. If it probably will explode, but even if it doesn't, it's going to take all day. So one of the things I like to do, there's a lot of different ways you can attack this problem, and if you go back and look at, I think, looking for the needle in the haystack that Jasper's done in the past on the retrospective, that's probably the definitive session on dealing with data sets, large data sets, using Trace Wrangler and other tools. But just quickly, things I like to do is take a big file, break it down into small pieces, and then have a look at one of the pieces and figure out what else I can do from there. Ideally, you don't want a bunch of files because you may have to go file to file to file to file to find the problem. You can't see the whole picture. So and there's other ways to do this. This is just the way I've always done it. So don't laugh if you do it a different way and you think this is dumb. I know a guy that, here's what he would do. When he was looking through log files, he would go more file, pipe to grep, pipe to more. I'm like, why do you do that? He's like, oh, it's just the way I've always done it. I'm like, well, it's dumb, stop. But he didn't. Anyway, we're going to read this file. We'll do the client side. We're going to break it into 100 meg pieces. -W. And we'll just call it like client.pcap. That's it, right? Okay, so now we have a bunch of files, 100 meg each. So we can open one of them with Wireshark. And it is here, here. Let's open the first one. Okay, so I also want to look and see, is there anything else I can do to help get the data smaller, right? So I'm looking at this, and I go, okay, they're probably 8960. Is that a number that jumps out at you, right, for the segment size, TCP segment size? They're probably using jumbo frames. He told me this is on in their lab. I think they were reproducing this issue. High throughput, multi-gigabit. So they're probably using jumbo frames. That's not a big deal. But we look at what we've actually captured, and we've captured 1,500 bytes of it. Do I need all 1,500 bytes for an NFS issue? Maybe, if I have to look at the application layer. But probably not. He said, we think it's a TCP issue. So what we can do is trim these down. So we'll look at this one here, and we've got Ethernet, IP, TCP. We look at the other side. We've got Ethernet, VLAN, IP, TCP. So what we can do is say, all right, well, we've got Ethernet headers, how long, how many bytes? 14. VLAN is 4. IP, 20. TCP, 20. Options, let's just say 20. 78 bytes, how about that? Does that sound good? So to do this, you can use edit cap with a snap length of 78, and we'll use the original file and call it snap.pcap. Okay, and that one now is 128 meg. All right, so we went from 950 meg to 128, and it's all in one file. Hopefully, Wireshark won't choke on that. And it is this one. So it's a little slow, but it's manageable. So first things first, conversations. We have a single TCP connection, good. Port, the NFS port, right? We have, 12 gigabytes of data. Let's see, through a handshake? No, we don't have through a handshake. That's unfortunate. I admonished my friend, how dare you give me a PCAP with no through a handshake. He did know the window sizes, the scaling factor, so you can type that in if you want as within Wireshark to manually set it. I'm not going to do that. So not great, but let's see what we've got. So we know we've got, we're dealing with jumbo frames, NFS. Let's look at our graph. Okay, and that looks different. Yeah? Not quite up and to the right as we expect. Honestly, this is the first time I had ever seen a graph like this. So if we zoom in, we can see that, we have data, right, going up and to the right really quickly because it's a LAN environment with gigabit throughput or more. But then it drops way down here and goes back up again. And it does it twice before we hit this dead spot, which is probably the hang, right? We're looking for a big flat spot in our graph, because if nothing is happening with a hang, then it's just no data is really moving. So that's probably that, and we'll get to that. But what is happening with this first part? Does anyone want to take a guess? I'm sorry? Yeah. Yes. So the sequence number is a 32-bit integer, unsigned integer, right? So it can only communicate, that many bytes, 32 bits. And once it hits the highest value it can get to, it rolls over, right? So let's have a look. I guess we can, let's go down here. And give me a moment to zoom in to the bottom. We're almost there. There. Now, you click on, I thought I mentioned that before, you can click on a packet in this, and it'll take you there in Wireshark. So we're there. So the sequence number of this is 43,000 and change. And right before that, it was a big old number. Oop, no, that's not the right side, sorry. Here, that's just an ACK. There we go. There's the last bit of data. So we've reached the maximum with this bit of, also, we saw jumbo frames before, but what is this about? 49,000 bytes in one packet? Is that a problem? Is it broken? What does that mean? Yeah, offloading. Segmentation offloading. So this is a feature of the network card that is probably enabled by default. TCP, instead of having to break up the data in MSS-sized chunks, which is 8960, and giving it to, so the kernel giving it to the network card, it can say, look, here's a bunch of data, deal with it. And the network card can then break it up into MSS and send it off. However, when we capture, we're capturing between TCP, which is the kernel, and the network card. We can't see what actually goes out on the wire, so we've hooked in between TCP and the network card, so we're seeing what TCP is giving to the network card. So that's one reason why you want to capture on the wire if you can, with a tap or a span or whatever, because you actually can see what's on the wire versus here, which is not really what's on the wire. And it can make analysis challenging. So we sent this much data. The TCP sequence number rolls over. Is that a problem? Probably not. We're just sending a lot of data real fast. Yeah, we can, let's see, this was the, let's do that, let's do this. Zoom back out. Let's go to the top. We're going to try to calculate the throughput here by seeing how long it took. Oh, wait, I need to go to the bottom. This thing is so big, it takes so much data, it's zooming out, zooming in. Here we go. Okay. All right. We want this guy. That's close enough. So we go to this packet where it rolled over the first time, which is right here. Yes, right here, it rolled over. We're going to set a time reference for this packet. So make it times 0, right? So now everything after that starts from 0. and we'll go to the top of the peak. Way up here. Almost there. There. So to get there, that's where it rolled over again, is 10 seconds, 10.56 seconds. So if we say, we know we sent this much data, right? That's the maximum sequence number. Divide, oh wait, no, that's bytes. So times 8 for bits, that's how many bits. We can divide it by 10.56 seconds. That is bits per second. We'll do K meg. So that's what, around 3 gigabits per second? It's moving pretty good. And then it dies a horrible death. So let's go to that, what we're here for. This is unwieldy. Okay. Flat spot. So if you can see the little circle, which is, it kind of jumps to the packets. Kind of just take note of the distance between them. From here to here, to there, to there, and to there. What do you notice about that pattern? Yeah, it doubles. What do you think that is? Yeah, let's click on one. Ooh, there we go. So you can see the delta column, right? 195 milliseconds, 200 basically, 400, sort of 800, 1.6, yes. So we definitely are seeing typical back-off behavior for retransmissions. Now, each one, look at the sequence number, is a different segment. Is that typical TCP behavior to back off and send a different one each time? Is that normal? Or would you send the same segment and keep backing off? I think it's the same segment, but honestly, I've seen both behaviors, so I don't know if it's, I wouldn't call, because in the next one we have the same behavior, sort of a back off, but it sends a different segment each time. So maybe that's just how it works. So it's a single timeout for the whole thing, or is it per segment? From this behavior, it seems to be per segment, but I thought it was suspicious TCP behavior. So after all that, we will load real quickly the server side. Don't see it. Oh, I didn't do that one yet. Nah, we don't really need it. So I said, can you please get me a, we could dive in further here, but I really would like to see a through handshake, get a better idea of what we're working with. I didn't spend a lot of time on that, right? I was like, can you please do that? And that one is this one. I think this one was taken on a span, and it's atrocious in terms of, and look at the little cheater column. It's lots of stuff going on. He said they were having trouble getting clean captures from a span, but this one at least had the throughway handshake, or multiple throughway handshakes. So we want, I guess it doesn't really matter. It's just the same hosts. So, sure enough, we verified that we're using jumbo frames. We have a window scale size. On this side, same thing. But immediately, I basically stopped here, because we're definitely dealing with packet loss. We didn't really dive into it, but we saw retransmissions. We're definitely dealing with packet loss. And when I want to see certain things when we're dealing with packet loss. What's missing from our options? Selective acknowledgement. It's mostly, well, I say mostly, I mean, it's kind of default in most things I look at. It could be stripped out, it could be just not turned on. Also, we're dealing with sequence numbers wrapping, right? What is something else that plays into protection against wrapped sequence numbers? The timestamps, right? So I said, look, I'm a busy guy. I don't have time to dig into your stuff here. Go back, turn these things back on. You should have turned them off, and try it again. And guess what? It fixed it. So they opened a case with the Linux vendor, and they said, well, why, they slapped their hand and said, why did you just say, well, we don't know who did that, but that's how, they were recreating the customer's environment. It was turned off, so we turned it off. So there was a combination of selective acknowledgments, which allow you to tell the sender, hey, I need packet X, but I have all these other ones, right? In the TCP options field, on the acknowledgments, you'll see selective acknowledgments, and we'll see it on the next case study. So it's a big improvement in terms of performance when we have packet loss. So that, coupled with some sort of TCP bug issue on the Linux side, which they acknowledged and filed, caused sort of this deadlock issue. But you can avoid it if you just have the defaults on. Yes, how are we doing on time? 15 minutes, is that right? Crikey. Okay, let's hit these real quick. Takeaways. Don't disable the defaults unless you know what you're doing. I see people tweaking kernel parameters with time wait and recycle, and it's like, if you don't know what you're doing, really know, leave it alone. And certainly don't disable SAC unless you have a really good reason. Three-way handshake, very important. We've already covered that. And then the offloading piece, one thing I didn't show you because we're running out of time, on the receiving side, packets it was receiving were still showing up as like 20,000 bytes. I was like, whoa, that can't be right. But in this case, we're sending data to the NetApp server, and the NetApp, actually, I think I've got, is this it? Yeah. Large receive offload is the reverse of segmentation offload. Data comes in to the NIC, it can assemble it into one big honking one and give it to TCP. So it's a performance thing. Again, capturing on the client or the server is not ideal. We got one more, we'll try to do it. This one comes from an attendee somewhere. Are you here? Oh no, yeah, in the back. So, blank web page. We go to the website, it's blank. Or it's really slow, essentially unusable. Looking into it, well, the provider did make some changes, but it's the web app's fault. It's the developer's fault, and here's why we think that's true. I mean, you guys have never been caught in like a finger-pointing exercise? That doesn't happen, right? The network team says, we don't see any LAN issues, so it's this fault, it's their fault. Well, how about we look at the PCAP and we figure out whose fault it is? So we will do that. Client side. I like to look at, when I'm looking at PCAPs, ideally I get both sides, but I like to start with closest to where the problem is seen. So if I'm the client, I see the problem with my PC, trying to do a thing. I want to see what they're seeing from the packet's perspective. So this is the client side. Now this was already narrowed down to a problematic, what am I doing? Problematic connection. So thank you Thank you. I love it when I get a PCAP and they're like, hey, we have this problem and there's one TCP connection that they've already narrowed it down to. They just need help, maybe to explain what's going on. So through Handshake, very good. We have 1460, Windows Scale, SAC, okay. Then we have Windows Scale, SAC. What's missing there? MSS. What happens if you don't advertise an MSS? 536 is the default from RFC 879. I had to look that one up. Yeah, that's not ideal, right? I mean, is it a problem? Is it going to break it? No, it's just going to suck. So we have a web application. We have the through a handshake. We have, let's get rid of this. We have, let's get rid of, I don't think we need push bytes. Let's clean it up a bit. Through a handshake, and then we have like 1.2 second delay coming from the client to the server. Is that a problem? Probably not. If it's a web application, we're waiting on the client to send a GET request, right? So the time before that happens, it's really on the user or the browser. So we're not really worried about that, even though 1.2 seconds is a really long time in network time. We scroll down, we see those 536 byte packets flying around, but it looks okay. And then I stop because I have a coloring rule, and I go, huh. And this coloring rule, you can look and see how it's colored. It is time delta displayed is greater than 190 milliseconds. That's some value I was using in a previous thing, and I just left it, and it's fine. You can spot, delayed acts and stuff. So let's look over here. We have 300 and something milliseconds. Okay. 900. 3 seconds, 12 seconds. That's not the typical back-off behavior, right? 48. But the numbers still, these values and how they are kind of sort of related in their intervals, should be, as a network troubleshooter, that should raise a flag to you that that's not an accident, probably. So we have these delays. It doesn't look like, we've lost anything because we can do the sequence number analysis. If we have this one, so this one is, I'll just read the last 4 digits, 1284 with a next expected sequence number of 1820. The next one is 1820. Then the next one after that should be 2356, and that's what shows up. And it continues on this nice little zigzag. You can follow it. The packets are showing up in order. And we're acking them immediately because we've waited so damn long for them to show up. Like, yes, please, give me more information. And then we do have a TCP previous segment not captured, and we can see that this is 5572, and the next one is not 5572. So if we do the math there, that's 536 bytes. So apparently we've dropped 1, okay. But then the delays kind of go away, right? And then the dupe acts start. This is where we're talking about selective acknowledgement, saying, hey, I need 5572. I've already told you that, and you sent me something else. I'm telling you again, I need 5572. Okay, now you get this one, 1468. No, I need 5572. And if you go down to the options, you can see a selective acknowledgement block saying, hey, I need 5572, but I have these. And as you go down, you can see for every segment that's received that's out of order, we keep changing the right-hand side of the SAC block. It keeps increasing for all the ones we've received. And I believe somewhere down here, so all those packets we're receiving, we're acknowledging, but we're saying, hey, I still need 5572. And then down here it shows up, 5572. We have some more like minute delays, and then finally the server is like, I don't know what's going on with you, I give up. And we close the connection. So the time here, we're talking 3 seconds, 12, 48, 60, 50, and then more at the bottom. If you click on a web page, what are you going to see during all this? Probably a blank page. So we have definitely captured what appears to be the issue. So, luckily for us, let's go check out the server side and see what it looks like over there. So this is that. We have our three-way handshake. Let's do this. Let's just kind of cut to the chase. This is the first one that was delayed, right? So we will copy that sequence number, copy as a filter, go back over here. Now I don't want to filter and just see that one. I just want to find it real quick. So you can use find, put it in there, and then you found it. So there it is. Do we see a delay here? Oh, well, there's, 1 millisecond? But the ones that come after it, right, this 2892, that was probably the next one, 2892. These have big delays. There's, about 6, 7 packets here. We don't see any of that over here. So that doesn't seem to be the server that is causing these delays. We can scroll down. We see something's happening down here. So this is where we start. Oh, this is, yeah. So that's the one we were looking at before, right? 2356. We have a retransmission of that one. Okay, so let's see. If we go back to the first time we send it, here, we set a time reference. So now that's time 0. Go back to where we retransmitted it. It's exactly 350 milliseconds. So we're just happy sending our 536 byte packets out the door over and over and over. We get to a certain point, we go, wait a second. I haven't received an acknowledgement from way back then. I'm gonna stop. So we stop with this packet, and we wait 295 milliseconds for something to happen. No ACKs are coming back, so we give up and go, well, I got to start retransmitting now. So I send a retransmission of back where the ACK stopped. All this other data is already gone. It's already out the door. There's nothing we can't get it back. We already sent it, but now we've got to start retransmitting the ones that have not been ACKed. So we get acknowledgement for it, right? The next sequence number is 2892. We get an acknowledgement of 2892. So, okay, good, we got an ACK. I can send 2 more. So it sends 2 more in sequence, because we're sending all these packets. We got 5052. So we pick right back up where we left off, and we're allowed to send 2 packets, because we got 1 ACK. And we wait, right? And there's the 800 and something milliseconds. And a packet from way back up there was never ACKed, so we send it. It gets through. It gets acknowledged. So we send a couple more. So there's something very interesting going on here. If we go back to the top, this is one of those times where you can actually look at IP. Each packet has a little identifier called the IP ID. So this one is 3506, right? This packet. 3507, 3508 is incrementing by 1 for each packet it sends. Now this is across the whole IP stack for every connection. So if they're sequential like this, then the server maybe it's not too busy talking to other people, other connections, but we can see that these are being sent in order. And is that the one? Yeah, that's the one. So this 2356 is the one that got dropped. Didn't show up, or it showed up really late. And it is 3508. So if we go over here and we click on that one, and we close this, and we open this, That's not it, right? That's a different IP ID. So which packet is that? Let's go to the second one. Here's the retransmission, 3744. Was that it? That was it. So the first one didn't make it, but the retransmission did. And if you look at the time that we sat here waiting, so I'm the receiver, I'm getting data, I'm acknowledging data, and the data stops coming for 364 milliseconds. Remember, our timeout was 350 milliseconds. That's pretty close. And this retransmission gets through. We're like, oh, great, something showed up. I'll acknowledge it. And then we wait again. Meanwhile, on the sending side, it's been sending data the whole time, right? And then it had to stop and go, wait a second, I'm not getting acknowledgments, but it's already sent a bunch of data. In this one, let's see, we can copy this one. All right, we got to wrap up. This is the retransmission. Its IP ID is 31153. And we click on it here. 31153. So again, the retransmission got through, the other one did not. Now, let's go back down here where things pick back up. So all of a sudden, we had this weird packet after these long delays, and then all the data starts coming through. This IP ID is 30606. And if we copy that, here it is up here. And look, 30606. This happens. Here are the packets that were held up, but were actually lost and never showed up. Their retransmission showed up later. And after that happened, the packets that were sent later all came in at once. So, to recap the situation, we had packets being sent, they stopped showing up. When they started timing out, the retransmissions themselves got through, and then after a few of those, 6 or 7 of those, the data started coming through. And you can do the IP ID analysis to see which are the original packets, which are retransmissions, and the order that they're sent. So that is very strange behavior. So we know there was a change. You lean on your provider, and they say, well, we did install this inspection device that inspects layer 7. And probably one of the only times I've seen weird behavior like this, where things just stop flowing, and then weird retransmissions get through. One will pop out, and then it'll keep going, and then it stops again, is like an IPS or something like that. It's doing some kind of application layer inspection. It needs all the packets to do its inspection. Do I allow this? Do I not? For the HTTP information. So you have this data. You have both sides. You know what you sent, and you know what you received, and it's all out of whack. You take this data, you take the analysis, get on a WebEx if you have to, and you take the provider to school and say, go fix this. And sure enough, there was a bug in the probe that they had in their network that was causing this problem. They fixed that, the problem went away. I would have probably gone a little more in depth on that one, but maybe next time. Actually, these 2 case studies, I'm probably will record back at home and put them up on the website, which I haven't put anything on the website in a long time, so that'd be cool. So the takeaways here, again, know the basics. The MSS thing, it's like, what is that about? That's a feedback you can give to the server team or whoever, and maybe they can even improve performance more. Get captures from both ends when you can, and lean on them, man. Don't let them get away with that shit. All right. Any questions? Actually, you can come talk to me afterwards. Please fill out your survey in the app. If you want to talk packets, send me an email or Twitter or whatever. Thank you for coming. I'll be here all week.